So welcome. So this is the next chapter, which is going to be on gases and plasmas. And what we're going to see with this is that, okay, solids, you can't make them change shape and you can't compress them. And then liquids, you can make them change shape, but you can't compress them. And now gases, you can make them change shape and you can compress them. So it's like the next in the sequence of desirable properties. And we're going to talk about the atmosphere. We're going to talk about some things like Boyle's law. We're going to talk about ionized gases, which are plasmas. So we start off by saying, like liquids, gases are fluids. They can go from place to place. Let me come back here. So gases are fluids. They can flow, they are compressible. A gas expands to fill the space available, and a liquid doesn't. It sticks at the bottom of the container. Molecules are further apart than in a gas than they are in a liquid. So we'd say there's no cohesive forces in a gas, whereas in a liquid there are cohesive forces that cause it to form droplets and the like. A gas particle typically in a beaker does not know that there are other gas particles around. It basically bounces from one wall to another wall to another wall. Whereas a liquid can spend most of its life in the middle and never know it's in a beaker. It'll just be hitting its buddies and kind of staying there. In an atmosphere, there's so much that they hit each other. You know, they eventually hit each other, but not in a smaller container. Yeah. So the cohesive forces are irrelevant with gases. They don't get close, so there's not this like droplet forming aspect. Gravitational forces are only significant for large bodies of gases like the atmosphere of the Earth or the substance of a star. If I took a mixture of, say, sand and water, gravity is such that the sand will sink to the bottom and the water will float to the top. Yeah. If I took two gases and mixed them, you would not notice any appreciable separation. You wouldn't get one gas on the bottom and another gas on the top. Although I had a job once where we had to deal with gases, and there were cylinders that contained mixtures of gases, and my boss made me roll the cylinders around it was on a rooftop actually, roll the cylinders around on the rooftop to mix the gases thoroughly. And I was never convinced that I was really doing anything with scientific merit. I felt I was just making my boss feel better because he was worried about it. But, you know, gases basically, it's very hard to separate gases, and gravity by itself won't do it. So here's a picture of our atmosphere, and just to give you an idea of the scale of the atmosphere, then we have aeroplanes fly around here, and most of the atmosphere, 90% is below. Divide things by 2, so 10 kilometers is about 5 miles, and 20 kilometers is about 10 miles. We say the atmosphere is about 20 miles thick, so it's like that. But, you know, Mount Everest is 5 miles tall. Planes fly at about 5 miles. There's a fair amount of atmosphere below you at about 5 miles. Temperature's getting colder as you go higher. So that's why you've got to have insulation in a aeroplane. The thickness of our atmosphere is determined by the kinetic energy of the gas molecules, how fast they move around, and the gravitational force caused by the Earth. So gravity is trying to squish the atmosphere down, and the kinetic energy is trying to boil the atmosphere up. So there's an equilibrium between those two. If the gravity were to increase, then the atmosphere would get denser and it would be lower. If the temperature was to increase, temperature goes with kinetic energy. So if the temperature was to increase, the kinetic energy would increase, and the atmosphere would get less dense and extend further. So there's this balance taking place. It's the same balance on the sun that determines how big the ball of the sun is that we see. It's the heat of the sun is trying to blow the ball up, and the gravity of the sun is trying to pull the sun in. Where those two effects balance is the size of the sun. We get a similar kind of effect for our atmosphere. Kinetic energy is primarily provided for us by sunlight, although not completely. We also have sunlight. We also have the energy of formation when the Earth kind of formed, and also some radiation, some radioactivity inside the Earth. A typical air molecule travels at a tremendous speed, 800 miles an hour basically. Tremendous speed. But it doesn't go anywhere. For every one going that way, there's one going that way. And in the atmosphere, it eventually will collide with things. So we don't notice we're being hit by stuff that's going really fast. It's really light, for one thing. It's not got much mass. So we're not in danger of being damaged by it, but it goes a lot faster than people think. We live at the bottom of an ocean of air. If we evacuated the air from inside a container, the outside pressure of the air pushes on it. So we say a vacuum doesn't suck, it just basically, the pressure of the atmosphere pushes. Just as water pressure causes the weight of water, it's caused by the weight of water above, so air pressure is caused by the weight of air above. At sea level, 1 cubic meter is about 1.25 kilograms, which is about 12 apples. I remember 12 apples. So a bag of apples, that's about the mass, or if you like, the weight of 1 cubic meter, 3 by 3 by 3 of air. So it's not got no weight. It's not got no mass. Substance is there, so it must have mass. And if you have a mass inside a gravitational field, you got weight. So it must have weight. It's just the fact that there's weight. Again, we're used to it. It's like we push out as much as the thing pushes on us. The weight of a column of air above a 1 square meter area is 101,000 newtons, or 101,300 apples. 1,300 apples. A newton is an apple, basically. That's, when you think about it, a lot of apples that are pushing down on you, but you don't notice them. If they were taken away, you'd blow up. Yes?
You say it's hard to separate air, but I read somewhere it says that when a fire situation, that you have to stay close to the floor too, because they have more oxygen.
Yeah. Yeah, so what am I saying there? What I'm saying, well, I think partly those gases that are from the fire are hotter. So they're going to rise in the room. Yep. And the gases that were in the air in the room will tend to stay lower. Okay? But if it was just that the atmosphere sorted it out in terms of its weight, in terms of its mass, then we would have, if you think about it, the atmosphere contains what? Nitrogen, oxygen, carbon monoxide, carbon dioxide, and things like argon and stuff like that. And they don't form layers in the room. You know, you don't get the lightest one on top and the heaviest one on the bottom. They just stay mixed together. Yeah. So I think that under normal circumstances, you don't have to worry about, you know, this is 28 and this is 32 and this would be 12 and 16 is 28 and this one is 32 and 12 is 44. You don't have to worry about the carbon dioxide all just going low and the oxygen going high. They're going to stay mixed together, you know. So I don't think it's a significant effect. When you have a fire, the stuff that's coming out of the fire, the poisonous stuff, is warm because it's come out of the fire. So I think it tends to stay high. So you stay low because there's less of those noxious gases when you stay low to the floor. I think that's it. But I've not thought about it as much as I should have done. So what is the approximate mass of a 12 by 12 by 12 room? Oh, man. Okay. It's basically, what do we say? 4 by 4 by 4 levels. So it's going to be 4 by 4 by 4, which is 64. And it's 64 times the mass of 1 cubic meter, which is 1.25 or thereabouts. So it's going to be 80. I don't want you to be able to do that on a test. I just want to show you it now. Why doesn't air pressure break windows? Because it's equal on the inside as the outside. We have a barometer. A good old barometer is basically, well, I don't show you. The simplest form of device is the U-tube manometer. It's just a U-tube and you have water or mercury or something fluid inside. And if I blow down on this side, it will tend to raise the level. So I'll end up with an imbalance. There'll be a column of excess water on one side. And the pressure of my blowing is balanced by the pressure caused by that fluid. So I can say let's call this P absolute. P absolute will equal the P of the column, which we call our gauge pressure, plus the P of the atmosphere, because there's atmosphere here. And that's fine. But the problem is, on different days, we have different atmospheric pressures. So a U-tube manometer is great for general stuff, but not good for precise stuff. It gets across the idea of it. If you want really good precision, you need to get rid of this atmospheric effect. And so what they did was they said, let's take a U-tube manometer, but let's not have this open to the atmosphere. Let's have a vacuum there. Now, how do they make it? Well, that's another issue, but they can make it. And so now you get the pressure on this side, the P absolute, if you like, on that side, is equal to just the P gauge, because there's no atmospheric pressure on this side to push down on you. So it's a purer type of device. It's a bit more complicated, but it's a purer type of device. And that's called a barometer. And barometers actually then become really good, because if I want to measure the atmospheric pressure, I just have a vacuum on one side of the tube, and I have atmosphere on the other, and my absolute is behaving here. So it's a way of measuring the atmospheric pressure. And people like to do that. It's kind of like people, nowadays we look at our phones, but back when I was a kid, every house had a thermometer and a barometer as like a wall ornament. It was like if you went on vacation and you couldn't think of anything to buy grandma, you'd buy one of these little wall plaques. So everybody has one. And they didn't work that well, but it was okay. Because people had a curiosity about, man, it feels hot, I wonder what temperature it is. And you couldn't go to your phone, and there was no computers, so you looked on the wall. And also there's this, people get these patterns about the weather, like, oh, it's low pressure today, good weather's coming. And they even had the barometers with like weather indicators. I mean, I remember seeing it rain like crazy outside, and the barometer would be pointing to fair, because it's got nothing to do with it. It's like so complicated, and this is such a simple device. It kind of works, but it's more for fun. It's like one of those, you see them occasionally. You see these like games you play, and there's this little note saying, this game does not predict future capabilities. It's just for fun. It was kind of like that. But people would have them all over the house, and mercury is not a good thing to have around the house. Again, when I was a kid, they would play with mercury in grade school. They would. It was such an unusual substance. It's a fluid, but it's heavy as could be. It's heavier than stainless steel. You can take a ball bearing and drop it in mercury, and it floats. I mean, that's the first time I saw that, I was just shocked. This steel ball is floating in this fluid. I didn't think steel could float, you know, it's floating in this fluid. So the teacher would come around and he'd drop some mercury in your hand and you'd play with it and you'd drop it and it'd go onto the desk. And frankly, you'd be breathing the vapors and the next kid in the room would be breathing the vapors and the next kid in the room would be breathing the vapors. And, you know, that might explain a lot about my generation, but we had mercury all around. And now people are so careful with it, and rightly so, because especially with children, it can be a real issue. So we tend not to use mercury anymore. We don't need to use mercury. There's much better ways of measuring pressure than this. Electronic ways, where we look at capacitors, basically. So this is history in a way. But basically, if we used a barometer, we can measure atmospheric pressure. If we use mercury, we only need about 2 feet of the tube. Basically, it's 2 feet high from there to there. If we use water, then we need basically 31 feet. So we don't tend to have many water barometers. But historically, that's where our pressure measurements came from. So we talk about inches of water or millimeters of mercury or the like. When really we should have been talking about pounds per square inch, or what we use now, newtons per cubic square meter. So these are science-related units, and these are observational units. And they both work. It's just, you know, it's better to have the science-related unit. So you use a suction pump. You can raise the water by a maximum of 31 feet. So that's an interesting point. You want a well in your backyard. You dig down to where the water table is, and you start basically. You put a pipe down there. You put a pump on the pipe, and most of the time it will not work, because if you just remove the air from above the water, you'll raise it up to 31 feet, and you can't do better than that, because you're not drawing the water up, you're just letting the atmospheric pressure push the water up. There's atmospheric pressure there, there's no pressure there. You can do that. So what you do is you put the pump down here in the water. Now you can pump up, and you can pump up very high distances, because you're pumping on water, you're not pumping on air. So it's an interesting ramification of that. If you want to draw water to greater and greater heights, you need to put the pump at the bottom of the well, not the top of the well. Okay. Let's talk about gases and playing with gases. So there were 3 people. There was Boyle. Then there was a guy called Charles. And then there was a guy called Gay-Lussac. He was French. And Boyle did the first experiment. He changed the pressure versus the volume at a constant temperature. Now, how did he do that? He just did it slowly. So if the gas got hot, he let it cool down. If the gas cooled down, he let it warm up. If you've ever pumped a bicycle pump vigorously, you feel it get warm. That's because you keep compressing the gas. If you've ever used an aerosol can a lot, you feel it get cold. That's because you're expanding the gas. So, okay, he did it at constant temperature. And what he found was the ratio of the pressure times the volume is always the same, as long as you don't let the temperature change. And then, just by the by, along came Charles, and Charles did the pressure versus the temperature. And then along came Gay-Lussac, and he did the pressure versus the temperature at constant volume. And then Gay-Lussac did the volume versus the temperature at constant pressure. So the 3 bits were done. We only talk about the first bit, which is P1V1 equals P2V2. So if you plot a graph of this, you'll find as you plot the graph, you get an inverse relationship. So let's go back. If I double my volume, so I have a syringe. and I have a trapped volume of gas. Everybody okay on a syringe? You know, like you go to the doctors and you get an inoculation. I have a trapped volume of gas. And I can squash on it. So I squash on it, and I have the volume. So if I halve my volume, I double my pressure. That's what this is telling me. Yeah? That pressure, P1 times V1, is equal to P2 times V2. Yeah? Okay. If a piston is withdrawn, pulled away, so that the volume of the cylinder is tripled, what happens to the pressure? P1 V1 equals P2 V2. Some people can just see this. They say it's got to stay at the same amount. So if I triple my volume, which is multiplying it by 3, to keep it back at the same level, I got to multiply my pressure by 1/3. 1/3 times 3 is 1. So this would be pressure is 1/3. Some people it's just like easy. For others, we got to figure stuff out. So what we say is, this is what you do. You go 1 times 1. I don't know what numbers they are, so let's just call it 1 and 1 is equal to now. The volume is triple, so that's going to be 3. So there's my P2. What do I multiply 3 by to get 1? 1/3. So it's the same answer. This is the formal way. This is the informal way. And some people just feel comfortable with it, and other people don't feel comfortable with it. Okay? If a piston is withdrawn so that the volume of the cylinder is halved, what happens? P1 V1 equals P2 V2. Do you want to have a go at this one? Let's see if we got it. How many people have got the clickers? Yeah, okay, have a go. Let's just briefly. So what we're going to do is, it really shouldn't be withdrawn, by the way. It should be squished in. Withdrawn is pulling out, squished in is pushing in, yeah. So if a piston is squished in so the volume of the cylinder is halved, what happens to the pressure? I've got 5 people. Let's stop it there and let's see. Yeah, pretty well. We're okay on this. So basically 1 times 1 is equal to, and I made this halved. So that's a half. Oh, that must be 2 times. So that's going to be doubled. Cool? Oh, it goes on. If the piston is withdrawn, so the pressure in the gas is halved. So 1 times 1 equals the pressure, which is 1/2. What must have done to the volume? Well, it must be multiplied by 2. So the volume must be doubled. Agreed? If the piston is withdrawn, so the pressure of the gas cylinder is quadrupled, what must you have done to the volume? Well, quadrupled is 4 times. So 1 times 1 is equal to 4. Must be times a quarter. So it must be quartered. And as I've said before, if when you're in the test and you're dealing with tripled, quadrupled, quartered, you know, that's fine. I can sort out, I can tell you what that means. I can't tell you what density means. That's a technical term that we all should know, but for stuff like that, colloquialisms like that, I can deal with it. Okay, so we talked about buoyancy to do with water and dropping bricks into it. Now what about density as far as the atmosphere is concerned? An object surrounded by air is buoyed up. There is a buoyant force because there's a displaced amount of atmosphere outside. There's the weight of the gas inside and the structure. And this will be my FG, and then we have our FB, and it's just like we had for throwing a brick into a pond or styrofoam under the water. If the object is less dense than the air, then it will rise, just like styrofoam does. If an object is more dense than the air, it will sink. If you read the book, he goes crazy about this. And he makes so my only criticism of the book is that he talks about some incredibly interesting stuff that I'd never thought of, which I think is great, but I think for a fundamental physics course, it slows you down a lot. So you end up doing a little bit of physics in a lot of detail. And as I say, I've not taught this course in a few years, and what I'm reminded of is that you don't get through much of the book. I actually went back, when I did this, I went back to one of my earlier versions of the notes because I wanted to mirror the chapters one at a time. And I got later versions of the notes where I do much more of the book, but I merge chapters together and I cut things out, and I don't care about this. And I just felt, because it was the first time coming back to this in a long time, I wanted to enable you to look at the book if you wanted to and just follow along much more. As you go away from the book, it's harder to use the book to follow because not all of it's relevant anymore. But the problem is it gets to the stage where it's too much stuff is in that book. And this is one of those cases where he does something, it's comparing soft-sided balloons. You know, the thing like we have we have the balloon and we have the basket and it's helium filled, or it could be hot air, but it can expand and contract. With a blimp like they have on football games, which is a structured balloon, and it cannot expand and contract, it just stays the same. And how they behave is to go higher and lower and all that kind of stuff. And I don't really care about it. If you're interested, read the book, but it kind of doesn't lead anywhere. It takes time up, so that's as far as I'm going to go on this. But the book goes further. Is there a buoyant force acting on you? Well, you're not a balloon, but is there? You bet there is. You're displacing fluid, the air. The air wants to be lower. You're making it go higher because you're more dense. So you bet it's pushing on you. And then, how does the buoyancy change on a rigid helium-filled balloon as it goes up through the atmosphere? I don't care about that. Okay, just forget about it. Okay. This is more relevant and it's kind of more interesting, which is when we take fluids like water, like air, and we send them through constrictions, the tendency is for the gas molecules or the water molecules to go faster as the cross-sectional area decreases. So as we get to a smaller and smaller cross-sectional area, you want the same amount of volume of stuff flowing down your pipe. And if it's got less area, it's got to have a bigger volume. So it goes faster. That's the tendency. You might think that this thing really slows down. And it certainly causes a bottleneck back here. But here it's going really fast. If you imagine 3 lanes going to 1, you know there's a problem when you're down here because the traffic's all backed up. But when you're going through this little bit, you go quite fast, don't you? You know, you've got the opening, you put your foot down and go. So what happens is, in the constriction, the velocity gets higher. So this is low velocity, and this is high velocity, and this is low velocity. And what's not so obvious is when you have high velocity, you have a low pressure. And I don't really have a nice way of explaining that. but it's true. You can observe it. I could talk about the molecules getting further apart, but you could draw the same diagram, have the molecules closer together. And if I'm drawing them further apart, then I'm messing with the density and all that, so it's complicated. But the truth is that when you get a high speed, you get a low pressure. This principle applies to moving fluids like gases and liquids, provided they have a laminar flow and constant density. Okay, so we're assuming constant density. Laminar flow means not turbulent. If you go out on a day when the breeze is nice and steady, that's laminar flow. That's like, it's just nice. If you go out on the day when it's blustery, when the wind is sputtering, that's turbulent flow. We don't know how to deal with turbulent flow. Mathematically, it's really hard. So we tend to ignore it. We tend to try to avoid it. It's not that useful to us most of the time. Sometimes it is. But we tend to model. We can't avoid turbulent flow. When we look at atmosphere, we're talking about turbulent flow. When we're looking at currents in a stream, we're looking at turbulent flow. So we need to be able to get mathematically better at looking at it. But it's hard. So when we visualize in things, we tend to visualize laminar flow, just layer upon layer. Like laminated plywood is layer upon layer, and the layers don't mix. So laminar flow is layer of air upon layer of air, and the layers don't mix. Where the speed of the fluid increases, the internal pressure decreases. So water speeds up when it goes through a constriction, and the pressure of the water decreases. We need to appreciate this, and we can use it, and we can guard about it. Here's a house roof, peak roof house. Here's wind blowing, blows really fast. This molecule wants to stay level with that molecule, wants to stay level with that molecule. So here, they've traveled further than that guy is. So it went faster. So the speed is fast here. So the pressure is low. So there's a tendency to lift the roof off a peaked roof building. It sucks shouldn't really say this, but it kind of sucks the roof up. So if you have a peak roof building and a high wind coming across it, it'll tend to cause lift. That can be structurally quite a problem. In Florida, since Hurricane Andrew, there were new constrictions about how much you had to tie your roof down in the house. There's new code. If you have an older house, they're not tied down as much as the new houses are. That's all right. That's living with it. What about using it? Well, here's a spray bottle. We try not to use propellants now, so we tend to use plungers and squeezy things, which is what was used before we got propellants. There was this period of time when we had propellants, and everything was spray. You had spray deodorant, you had spray foam for your oven cleaner, everything was spray. And it was using chlorofluorocarbons because they were inert, but they caused the ozone hole. So as soon as we realized that, they banned the fluorochlorocarbons. We found other refrigerants, which that's what they were primarily used for, that weren't so damaging. And we went back to spray bottles, you know. My finger's pretty strong. I can spray a whole lot. Whereas when I was in my teens, everything was spray, you know. It's like amazing. So this is an old-fashioned one. All it consists of is a tube which goes into the fluid, and a tube that goes along the top, and you brush the air out, and as the velocity increases, the pressure decreases. As the pressure decreases, it draws up the fluid. Eventually the fluid gets to the top and is sprayed out. So it's and maybe on the third squeeze the liquid comes out, and you know, it's very nice. Same principle, aeroplane wing. The wind comes, I drew it, of course, in the wrong direction. Can you believe it? Man, you don't notice things sometimes. So the air's going like that, and it's going like that, and it's got faster on the top than it is on the bottom, so lower pressure on the top than it is on the bottom, and you can pick an entire aeroplane up like that. Yeah.
Is that the same feeling like when you driving so fast, like you pass another car, it's like you feel like
So are you drawn into it, or are you pushed away from it?
into it.
Yeah, I'm going to get to that, yeah. That's right. You drive really fast. I noticed the same thing with, I had a little Honda 50cc motorcycle, and it was, most of it was fine. I was on a road that was relatively busy but well behaved, and every now and then I would have a big truck would go next to me, and the first shockwave would push me away, but then as it came by it would suck me in. So it was like really quite dangerous when the big trucks, the big high-sided trucks went by you. It was really bad. So down here, this is interesting. You want to hide? Bury yourself. You will suffocate. Not necessarily. If you dig a tunnel to the top of the hill and you have another tunnel to the bottom of the hill, by and large the airflow is faster the further up you go. So the chances are there'll be quicker air flowing there than there is there. There'll be lower pressure there than there is there, and the air will be drawn through. So you'll have a nice breeze through your subterranean little house. And it works. The golfers, I don't know this personally, but from what I gather, golfers designed their little burrows like this. So golfers do that. Now, sailing. If you go sailing, you notice that a lot of people have docks that stick away from their seawall. So they have I'm going to draw it this side. They have a seawall, and then they have a wooden structure, and then they have this is a dock, yeah? And so you park your boat next to the wooden structure. And I always thought, well, that's a bit of an overkill. Why do you need the wooden structure when you got the wall? Why not just park next to the wall, and then you can just step on and off from your garden? And it turns out that there's a problem with that. If I have a wall, looking down from above, if I have a wall and I bring my boat in to park it, there comes a point when the water's flowing really fast, as I'm trapping more of it. You know, I didn't draw this very well, but there's the pointed bit, and that water there has to go through there. And so it goes really fast. Going really fast means low pressure. Low pressure means. So the tendency is the boat will be drawn to the wall if the wall is there. But if I have pylons, then there's all this water here available to stop this effect from happening. So you don't try and park your boat next to a wall like that. And just in the same principle, you don't try and get two boats that are sailing too close to each other. You don't get ocean liners sailing 10 feet apart because they will collide. There's a thing called the bosun's chair. If they want to get personnel from one boat to another, they don't bring the two boats together. They use a big line between the boats, and the person has to, like a zip line, they have to go between the two boats because they can't bring the two boats together because they get that suction effect like you noticed with the two cars. It's like the bigger the boat, the longer the boat, the straighter the boat side, the worse it is. But even actually on when you're throwing a curveball, you throw a curveball by spinning it. And because the spinning of the ball is going in a counterclockwise direction, it's going really fast there, where it's going in that direction, and so the air is going in that direction, and let's see if I can get this right. The air is going in that direction, so this is fighting it, and on this side the air is going in that direction, Sorry, no, the air is going in that direction. So this is fighting it, and this is playing with it. This is going with it. So you get a low pressure there, a high pressure there, and so the ball tends to move in that direction. So when you throw a spinning ball, it will tend to move in the atmosphere because of this effect. True or false? Bernoulli's principle states where the fluid speed increases, the internal pressure decreases. Agreed? Agreed. How will the internal pressure in flowing fluid change as water speed increases? As the water speed increases, the pressure will decrease. Water flows through this section of pipe. That has a constriction. Which section of pipe will have a higher flow rate? What do you think? Is it flowing most quickly here, most quickly here, or most quickly there? B, yes. So B. And then water flows through the section of pipe that has a constriction. Which section of pipe will have the lower water pressure? B. By the way, bad questioning on my part. These two are symmetrical. So it's highly unlikely that either one of those would be the answer because they're the same. So a better question would have been only with A and B and A and B. That would have been a less obvious answer. Plasmas. You take a gas, and using some method, maybe an electrical field or maybe just plain electrical voltage, you cause the electrons to leave the atoms. So you get ions. You really get the gas in an excited state. The electron goes to a higher energy level. It only stays there for a split second and then it descends. When it's in the higher energy level, it has to have the right amount of energy. When it's in the lower energy level, it has to have the right amount of energy. If it wants to go from the high to the low, it's got to get rid of some energy. It's only got a few mechanisms, and the mechanism that it chooses is it emits a photon of light. Not just any old photon, but a photon with a specific color, because color is energy. That's what determines the energy. So with neon lights, you know, a neon tube is filled with neon gas, not filled, but it has a partial pressure, a low pressure of neon gas in there, and neon gives that characteristic orangey kind of color. It's not the tube that's colored that color, it's neon that gives that color. And if you want a different colored tube, put a different gas in. There's a whole variety of gases you can pick. You get a whole variety of colors depending upon what gases you fill the tube with. And the color is indicative of the gas. So you can look and you can say, oh, that's hydrogen, that's helium, that's neon. You can tell them apart. So we can make plasmas deliberately by having a partial pressure of gas and then using electricity to cause the excitation. Nature sometimes does it. The nature sends a whole bunch of cosmic rays from the sun, charged particles from the sun. And they, on occasions, hit our upper atmosphere and excite the atoms in our upper atmosphere. So we see the northern lights. If the Earth is here, the cosmic rays come in and they follow the magnetic field lines. And the magnetic field lines tend to direct them to the poles. So you tend to find the northern lights occur in a band around the North Pole and the South Pole. And so people in Canada see northern lights much more frequently than people in upstate New York and, you know, North Carolina very rarely sees northern lights. I don't think they ever see them, and so on. In my childhood, I never saw the northern lights, and I was actually level with the Hudson Bay in Canada. England's level with the Hudson Bay. So if I'd gone to Scotland, you see them much more frequently. So you have to go really far north to see them. So it's called the Aurora Borealis for the northern lights and the Aurora Australialis for the southern lights. Australialis sounding like Australia. So that's another source of plasma. We can get plasma near the sun. The sun is very high energy. It heats up the gas molecules surrounding the sun to a very high temperature. That causes ionization. Whenever you get ionization, you get this relaxation effect taking place. And so we see the sun with a very specific color. It's got that color because of the temperature of the gas. And then another place we might see them are jet engines. When you see that flame coming out of the back of a jet engine, that's also a plasma. We say plasmas are the fourth state of matter. We have solid, liquid, gas, and plasma. Plasma is an electrified gas, an ionized gas. The atoms and molecules that make up a plasma are ionized. Plasma gives off light, readily conducts electrical current, and can be shaped and molded by magnetic fields. So I can make this plasma form a pattern if I want. Got questions. What are the states of matter? Solid, liquid, gas, and plasma, not earth, air, fire, and water. True or false, atoms and molecules that make up a plasma are ionized. That's true. True or false, plasma is an electrified gas. That's true. True or false, a plasma gives off light, readily conducts electrical current, and can be shaped and molded. That's true. And when glowing, a neon light is filled with a plasma, and that's true. True, 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 true. Yes.
Right. So I'm thinking about the fluid, like the internal fluid, like any point fluid in internal fluid has two kinds of pressures. One is station pressure and kinetic pressure. Is that correct?
I don't know. What's the definition of kinetic pressure?
Well, kinetic pressure is like the things like depends on the velocity of the.
Oh, you mean the fact one running into another kind of thing? The fact that it's been pushed by the guy behind? That implies so. That raises a very interesting point. Why does gas or liquid flow? And that's because there is a pressure difference. So, yeah, there is the pressure of my atmosphere around me. And then there's a pressure difference which is causing me to go in a certain direction. I am trying to go from a high pressure region to a low pressure region to form equilibrium, really. Now, I don't think we tend to, it's a question of language. I don't think we tend to talk about it as being two pressures, a kinetic and a, I think we talk about it being a pressure and a pressure field. The pressure field is the difference in pressure, or a pressure gradient. So I think they would model it by saying there's just atmospheric pressure, what we might call the static pressure. But when there's a pressure gradient, we have a flow of matter from one place to the other. So I think you're right. I think it's just language, what terms you use to describe it. But I think you're right. You're seeing I'm being pushed in a certain direction. And that's because there's a pressure on me to go in that direction. Yeah? Cool. Very good. Okay, let's